When we graph a function of a real variable, we have two axes, x and y. All right? And so I can sort of graph like this. All right, and this gives me an input and an output. Now, unfortunately, if I want to use this same method to graph a complex function, my input requires two dimensions, the real and imaginary parts. The output will unfortunately also require two dimensions, its real and its imaginary part. As we'll find a little bit later on, all of the interesting functions of a complex number have to have non-trivial real and imaginary parts. All right? So we're not going to have a situation where we only have a real part for the output. Now, we could, if we wanted to, make a graph of just the real part versus the whole plane of inputs, and then just the imaginary part of the output versus the whole plane of inputs. Those two graphs would be surfaces in three-dimensional space. Okay? And you can actually look at those graphs. I've got a Mathematica notebook that we're about to look at that contains those in it. Unfortunately, those graphs rip apart the full complex function. All right, if you take the real part and the imaginary part and you separate them, you're doing violence to the function. And as such, you won't be able to see the relationships between those parts that really represent the heart and soul of that function. Okay, it's not the real part or the imaginary part by itself. It's more associated with the interplay between those two things. So that's not really a viable option for us. Okay? As a better approach, we could imagine graphing the input and the output separately. Okay? And so what we'll find is that maybe with an input being this rectangle, the output ends up being this sort of curvy region. All right? Now, this is not perfect. Essentially, this would be like just sort of graphing, if I wanted to look from here to here on this function, it would be like I'm graphing a number line, and I would go from here to here, and then the output number line would be like this. Well, let's see, it went negative, it went positive, then it went negative, then it went positive, then it went a little bit smaller. And that's what our graphs are going to represent. This, of course, is a much stronger view of what's going on, but we don't have access to that because we don't have 4 dimensions to work with. All right? So let's see what some of these maps look like. This is a Mathematica notebook that I have not yet put up, but I will put up on Blackboard this afternoon. All right, so that you can look at it at your leisure. All right? With a lot of these math books, a lot of these Mathematica notebooks, I talk a lot. You don't need to read all of this, but you can if you want to. It's like me doing class again. All right? These are the complex maps. All right, so here is my input. This oops, there it is. There's my input rectangle. All right, and now I'm going to do z squared acting on this input rectangle. And it gives us this region, similar to what I graphed on the board. Okay? Now, if you look at a mesh for this, these curves represent curves of constant x and constant y in the input plane. All right? And if you look at them, you'll see that they are perpendicular. This is a very, very important property of complex functions. And we'll see that for a number of different functions. Suppose that I wanted z cubed. All right, now this is going to be a little bit off because I had originally made this graph so that it would fit right. And see, now it doesn't fit anymore. But you can see that these curves, again, make right angles. Okay? That property is referred to as a conformal property of the complex map. A conformal map is one that preserves angles and orientations. All right, it preserves angles and orientations. So if I look here in my input, lines of constant y are horizontal, lines of constant x are vertical. So they make right angles with one another. If my map is conformal, then it must preserve those angles. So these can be curves if they want to, but the tangent lines to those curves must be perpendicular at every point of intersection. Moreover, I have to maintain orientation. Here's one way to think about what that means. If I start here and go around this box in a counterclockwise fashion, the interior of the box is to the left of me as I travel. Interior to the left. Here, it has to map in such a way that the interior is still to the left. So I could have this point map to that one, and this point mapped to that one. That is proper. That would maintain orientation. But if I mapped the other way, if this point mapped there and that one mapped there, the orientation would not have been preserved. Okay? So that would represent a mapping that's not conformal. If it maintains the angles, but it reverses the orientation everywhere, then it will be referred to as an anti-conformal map, the opposite of conformal. All right? So let's see another example. Oh, so this is an animation that shows how the rectangle becomes that sort of funny shape. All right, so let's see. There it goes. All right. I think I'm going to need to make it a little bit smaller, but we can see it all at the same time. All right. So I'm just going to go ahead and let this play out. Actually make it a bit slower, and I'll start it off at the beginning again. But you see what's happening is the rectangle is turning into that other shape, the output shape. We are stretching the rectangle and rotating it. So that should seem familiar based on what we talked about last time with multiplication being a combination of dilation and rotation. That's what squaring is. You're multiplying the number by itself. The difference between z squared and just, 1 plus I times z is that the amount of the dilation and the amount of the rotation depends on the value of z. It depends on where you are. All right? So parts of the box that are up here they're associated with a larger argument. All right, so they're going to rotate more. A part here is the biggest argument on the whole rectangle. So that's going to rotate the most. Okay? That's going to rotate the most. The part that dilates the most is the part with the biggest modulus, which is that point. All right? So these complex maps can be thought of in this sense as representing sort of a stretching and a rotation of a region in the plane.